I think people will come in as we continue talking. All right, so I'm recording now.
This meeting is being recorded.
Okay. Hi, everyone. Good evening. Again, welcome to class. So let me go straight and let me try and get the materials for tonight's class. If you haven't done so, please go to Blackboard. You will see under course documents, you will see 4 pages of notes, my handwritten notes on this topic. So that's what I'm going to do is 4 pages on Arch and GARCH. All right. Somebody is sending me. Okay. Um, somebody is sending me a chat. Let's see. Oh, Blackboard was down right before it was. Okay. Blackboard was down right before what was due. Okay. All right. Never mind. Let's see. Okay. So look, again, what I'm going to do tonight is I'll talk to you. Okay. I'm going to talk to you. So please try and stay with me in terms of concepts. And if I lose you, that's okay. Just ask me questions, okay? And I'll bring you back. Or if you lose me, then let me know and I'll let you know and we'll bring back each other. All right. So what are we doing in chapter 4? What is the idea behind chapter 4? All right. Let me, again, if need be, I will go to Excel, not today, but Tuesday. So Tuesday will be just Excel and R. But let me take your mind back to Echo 4000, everybody, okay? Echo 4000. In Echo 4000, what did we do? Well, we did many things in Echo 4000, but one of the important things we did was we said that if you want to find the relationship between X and Y, if Y is the dependent variable and X is the X variable or independent variable, then you can do correlation analysis, but correlation analysis will tell you how strong or how weak the relationship between those two variables are. That's fine. If we see that through correlation analysis that the relationship between Y and X is strong, that's okay. But then we want to know if we have X, if I give you X, or if you give me X, how will I determine Y? Remember, X is the right-hand variable, X is the independent variable. So if you give me X, what equation will help me determine Y? So what did we do? We said, well, let us assume that the relationship between Y, the dependent variable, and X, the independent variable, let us assume that the relationship between them is linear, yes? But the relationship between Y and X can be anything. It can be linear, it can be logarithmic, it can be quadratic, it can be cubic. But we say, okay, let us assume it is linear. That means Y equals A plus BX, where A is the intercept and B is the slope. And then usually when I teach econometrics, students will ask me, but professor, but what if it's not linear? What if it is quadratic? Well, the simple answer is if it is quadratic, we can make it linear. Yes? How can we make it linear? We can transform the equation to make it linear. One quick way of transforming it is what? To use what? Somebody sending me chat. To use what? Logarithm, right? So one way we can linearize this is to use ln. Correct, Danny? Andrew, sorry. Okay, so one way we can linearize is to use natural logarithm. Okay, so that's one way. That's great. So if something is not linear, but if you do log on both sides, then the relationship is linear in logarithm. So because typically we have only one semester with you guys, with students for Echo 4000 or for basic statistics, we don't have time. So we say, okay, let us use the time, the semester, to focus on linear models. But we do recognize that linear models could be not the actual relationship. That's okay. But if linear models are not the relationship, then that means once we run the linear regression, then the conditions will not be kosher. The conditions will not be the conditions, the assumptions we make will not be good. So we say to ourselves, let us discuss with the students, you and I, we discuss anytime you want to do OLS, ordinary least squares regression, where we assume that the relationship between y and x is linear. Anytime you want to do that, let us, that assumption of linearity will be good, and that model OLS will be good if some conditions hold. What are those conditions? That if you run the regression y and x, and you get the intercept and you get the slope, that the error term, or what you call the residual, we must make that the residual should behave in a particular way. That is, the average of the residual, the expected value of the residuals must be equal to 0. So if we collect the residual and we calculate the average, it should be 0. If we collect the residual, we calculate the average, and we subtract the average from each of the residuals. And as we subtract the average, we square. And at the end, we add up. In other words, if we calculate the average, it should be 0. If we calculate the variance and standard deviation, it should be constant. Somebody tell me you remember these assumptions. Yes, okay. Nobody's talking to me today. I feel like a lonesome dove.
Can you please repeat the assumptions, Professor?
Okay, okay. The assumptions to do in Echo 4000, the assumptions we made such that our OLS, the regression we run, it will be good. Whatever intercept and slope we get, the assumption we make in order for that equation to be good is that the residual, the error term, should be average 0, yes? And the variance of the error term should be constant. Whatever that variance is, it should be finite and constant. That is the assumption of, what was the technical name we use for it? That the variance and standard deviation of error term should be constant.
Homoscedastic.
Exactly. Homoscedastic. Homo meaning same. Hedastic meaning is variance, variation, variability. Hedastic, I think it's either Latin word or something. So homoscedastic meaning same, variability. So the variance and standard deviation must be constant. So with that, then you and I can run OLS anytime on Excel. All of you can do that because you have done that. We do that. Okay. But sometimes we do forget. So that's why I'm reminding us that anytime we run OLS, we get the equation, we get the intercept and the slope, A plus B. We get that B, A and B. And then we say Y equals A plus BX. That equation will be valid if and only if those conditions occur. That the residual will average to 0, and the variance and standard deviation of the residual will be constant. That is the homoscedastic assumption. There are other assumptions, but for now, that doesn't really concern us for now. I'm focusing on these two. All right. So how do we check? How do we check that those two assumptions hold? How do we check? Well, number one, when you run the OLS, what do? You ask Excel to give you the residuals. Yes, you can do that just by checking one box. I will do that on Tuesday. Don't worry about it. Okay, I'll do that. I just don't want to be distracted with concept and program. I will do that on Tuesday. So we're going to we run the OLS on Excel, and we check a box, and that box we say give us the residual. Okay, and then it will. At the end, we get the intercept, we get the slope, therefore we get the equation. And then for us to check, we generally don't do this, but for us to check, then we can go look at the column of residuals. So the column of residuals is really a column of numbers. So we can go at the bottom of this, the column of residuals, find the average, and check, is this 0 or not, okay? And then we can, the same column of numbers, find the variance, take the square root, find the standard deviation, and look at the variance and look at the standard deviation. We can do it across time and check if anytime we do it, that the variance is constant. If it is, then our OLS assumption held, and therefore the regression we run in Excel will hold, will be good. If it doesn't hold, then the variances will be different each time we do it. The variance of the residual will be different each time we do it. And therefore, that model, we cannot be confident using that intercept and slope we obtained on Excel. Okay? But you and I, we don't normally, how do we say? We don't normally bother with that because we learned in Echo 4000 how to analyze our regression results so that if the residuals are not good, then we will know without having to analyze the residuals themselves. We look at the t-statistics. If the t-statistics are such that we reject the null hypothesis or accept the null. So in other words, the t-statistics and the standard error of A and standard error of B, for which we use to calculate the t-statistics of A and B, and also the p-values, they all give us a hint about how good the residuals are behaving. Are they behaving as we assumed? Average expected value 0 and variance constant, okay? All right. The same thing in time series in financial econometrics. Anytime we think that, so we go to Yahoo, we download Facebook, or we download IBM, and we say that column, does it follow, how best can the return to that stock that we downloaded, does that return follow an AR model? Does it follow an MA model? Does it follow an ARMA model, Arma model? Whatever the model we think it follows, AR, MA, or ARMA, that model is what we call the mean equation. That is like our OLS equation in Echo 4000. But in order for that OLS equation to be good, we assume that the error term in that regression should be expected value 0 and homoscedastic. You agree? That's Echo 4000. The same way in financial econometrics, in time series analysis. If I want to run a regression and I think that the AR model is the best model to use for that stock, for these returns to that stock, then I'll write an AR model. If it's AR1 or AR2 or AR3, it doesn't matter, but whatever AR model I believe in, I write that model and I estimate it with regression. But in order for that model to be good, I have to make certain assumptions about the error term. Usually the error term we assume is white noise, usually. And actually, we go beyond that, Danny, because you're always asking me this question. We always assume that it is 0 mean white noise. So in other words, look at this equation. Look at on this page that I'm sharing with you now. Let me try and make it bigger. Everyone should have this handout, okay? It's been in your Blackboard since Tuesday. So suppose I have Y, okay? In case you're wondering what handout it is, it's ARCH models. It's in Blackboard now, okay? 4 pages. This is the first page. So suppose I want to run a regression of, let's say, IBM, a return to, so I go to Yahoo, I download IBM prices because that's only what I can observe. I change them to simple returns, and I say, I believe those simple returns follow an AR model. and I write the equation, this first line, equation 1, okay? And I say the return to IBM, y of t equals b1 plus b2, return to, I use x here just to separate y and x, to remind you what you did in Echo 4000. But suppose this x and this x and this x, that they are really, so yt equals a constant plus this constant times yt minus 1 plus this constant times yt minus 2 plus this constant times yt minus 3. That's an AR3 model. Suppose I make the assumption. Plus error term, which is white noise. For this equation, suppose this equation really represents the return to IBM, then this error term must behave like white noise. And by assumption, a zero mean white noise. And if I assume it's a zero mean white noise, that means the error term is 0 and the variance is constant, homoscedastic. But what if it is not homoscedastic? What if the error is not homoscedastic? What if you and I go and collect the residual? So we run this equation, we run this OLS equation, this equation, and we collect the error term, and we collect the residual, and we study the residual. What if the average is 0? So that's good. But the variance is not constant. That means the variance changes like t. So so how does the variance change? It depends on the time period. That's why we put the t here, okay? If that happens, then the error is no longer homoscedastic. That means this equation that assumes white noise error, it's no longer good. So whatever the coefficients are, B1, B2, B3, B4, those coefficients and those coefficients that we get using maybe OLS, those coefficients are no longer good because our residual shows us that the error is not white noise because the variance is no longer homoscedastic, it is heteroscedastic. No panic, okay? No panic. This B1, B2, B3, and B4, so this, what we call the mean equation, the mean equation will still be good if we do this. Before we run this equation, we need to track what equation describes this variance. Because if we say the variance is no longer constant, then the variance cannot be variance at time t equal to constant. It's no longer, because that's homoscedastic. So the variance has to follow a particular type of equation, okay? And in the technical language, we say the dynamics of the variance should be known to you and I. There has to be dynamics, how the variance changes from time to time. That's why we're sticking this little t. So it doesn't, so this mean equation, it doesn't mean that because the variance of the error term, the variance of the white noise is no longer constant, so therefore it's no longer white noise. It doesn't mean that that mean equation is useless. No, it's not useless. If we can find how does the variance change, we can find the equation, how the variance changes, and then use it, and then we use that equation every period to update, to capture the variance of the error term, and then plug in the variance of the error term in this equation, and then use it to determine y. So it's not bad if the variance of the error term changes from time to time. It doesn't matter. It's not bad as long as we can establish how does it change. What equation can we use to track how it changes? And so if we can get that equation, then every period we determine the variance of the error term, and then we use it to plug in to determine the error term and to determine this error term, and then we plug into this equation to determine y. So then we are running kind of two equations the same way, the same time, instead of one. In OLS, we are always focusing on this first equation because the variance of the error term was constant. So every time we run the equation, We use the same variance to determine the error term and then plug it into the equation, and we use it to do our OLS regression. But if the variance is not, if it's not homoscedastic, it is heteroscedastic, and we know the equation that is driving that heteroscedasticity, then what do? Each time, before we run the mean equation, the OLS in Excel, before we run this, we first capture the variance for that time using the variance equation. And then using that particular variance is no longer constant, but using that variance for that period, determine the error term, and then plug it into the OLS equation for the error. And then with that error term, we can determine the B1, B2, B3, B4. So when we have heteroscedasticity, it's not the end of life. Okay, it's the end of life in OLS. I'm sorry, in Echo 4000. But beyond Echo 4000, it's not really the end of life, because now we are running two equations simultaneously. Before we do the OLS, we first do the variance equation, heteroscedastic equation from time to time, because we know the equation that drives variance. So we determine variance of the error term period by period, use it to determine the error term period by period, plug the error term into this equation, equation 1, period by period, and then we use it to run OLS to determine B1, B2, B3, B4. That's the way it works. So chapter 4 helps us to determine, to see, how do we know exactly which type of equation captures the dynamics, the movement of variance from time period to time period? Because of this little t, okay, we know the variance of the error term is no longer heteroscedastic, it's no longer homoscedastic. All right. Okay, let me stop and see if anybody has a question. Is Alec in this class today? I haven't.
Yeah, I'm here, Professor. I'm here.
Okay, are you following me, Alec?
Yeah, I am.
Okay. Tobias, how am I doing so far?
Great, you're doing a great job.
Roxolana, I haven't heard from you. That makes me nervous.
I'm doing okay.
Okay. Hey, how about my buddy, Lily? Oh my God, if Lily is not here today, then somebody let us call FBI.
Lily stepped out because she has a flu shot today.
Okay, all right. Tell Lily that I asked for her because, so thank you, Andrew, for telling me that. Okay.
Yeah, no problem. She's my partner, my best friend. Tells me everything.
Okay, that's good. Please tell her to look at the recording later. Okay, so bottom line is, if we have heteroscedasticity in the error term, it's a problem, but it's not the end of life. Why is it a problem? Because we have to determine, how does the variance change? And that is the subject of chapter 4, okay? Now, how does the variance change? Let me give you intuition, okay? Okay, so I'm going to move away from this. I'm going to move away from this page, and I'm going to go to chat, okay? So I'm going to be sending you two things on chat, and I'd like for somebody to tell me what is the difference between the two things. Danny, you have your hand raised.
Yeah, the coefficient for arc models, it's still less than 1, right?
I haven't talked about that yet, okay? But we shall talk about that, okay? So y equals a plus. So Danny, hold on to that question. That's important. I will talk about that later, okay?
Okay, so the b's are not the coefficients of the xt's, right?
No, the b's are not the coefficients.
It's something, okay.
It's something else, okay? So, but hang on to that. That's a very important question, we shall talk about that. Okay, plus b times, just bear with me, okay, everybody? I'm typing something for you on chat. Bx, okay, x. All right, so this is one equation. I just sent it to everybody on chat, okay? And then the second equation is coming, y equals a plus b times All right, what is the difference between these two equations? Anybody?
The error term, obviously.
Wait, who is talking to me?
This Alec.
I like my body. Okay, Alec. So the error term is a difference. Obviously, I like that word you use. Obviously, the error term is the difference between those two equations. Okay, but what is the implication of the error term not being in equation 1? Huh? Oh, no. Suppose I say y and x are related by equation 1. Okay? And then I say y and x are related by equation 2.
One is a prediction, the other is the actual
No. I'm telling you that two of them are actuals. Again, thank you for saying that, but my bad. So I tell you that two of them are actual equations. Which one tells us that all I need to do is give you x,
1.
and then you will determine y with 100% certainty. Which equation? Which one?
The first one.
The
the
first
first
one.
one.
Yes.
How about the second one? If I give you x, definitely, are you going to tell me that, Professor, this is using this x and knowing a and b, that this is definitely the y that goes with that x?
No, we need more information.
You need more information. And how do we express that we need more information, Nadia? We stick in that little epsilon. Is that right? That E, error term. Is that correct?
Correct.
Okay. So, Alec and Nadia and everybody else, equation 1, we say, is a deterministic equation. Okay? I mean, I'm sure you learned all of this in Echo 4000, but it's okay if you did not. That's okay. Or if you don't remember. It's a deterministic. So equation 1 is deterministic. By the way, those of you that studied physics, most of physics is like equation 1. Most of physics, because physics is a physical phenomenon. When I was studying physics, we were dealing with certainty most times. How about equation 2? What technical term do we use with equation 2? Huh? We use uncertain, or if you want to be, how do you say, fancy, if you want to impress your friends in cocktail parties. By the way, if I see you guys in cocktail parties, you will not know me the way I talk, okay? Because I use the term you're going to say, who is this? I use the term stochastic, right? So the second equation with the error term is stochastic. That's the term we use to indicate stochastic or uncertain, meaning that if you give me x and we know a and b for equation 2, the y, if I plug x into that equation, the answer it gives me as y. If you give me the same x on another situation, the y might be different. Okay, so why am I saying this? In chapter 4, okay, in chapter 4, when we determine his studies before going to cocktail parties for sex, I don't study. My head is full of all kinds of BS. So if you see me in cocktail parties, my BS, that's my BS talking. Okay, so if in chapter 4, so whenever the error term is heteroscedastic, it's not homoscedastic. If it's heteroscedastic, there are two families of equations that we can use to describe the variance. There are two families of equations. One family of equations is like equation 1 on your chart. So one family of dynamics of the variance term, that is the equation we use to track how the variance changes. there's one family of equations that is deterministic. Another family of equations is stochastic. Let me stop here. Do you understand what I just said? If the variance of the error term is no longer fixed in our OLS equation or in our mean equation, if the variance is no longer fixed, but the variance of the error term has that little t below it, that means it's not homoscedastic, it's heteroscedastic. No longer constant, changes from time to time. How does it change? Well, there are two families of equations that help us determine how the variance changes. Two families of equations. One family is deterministic. The other family is stochastic. Are you with me? Chapter 4. Chapter 4 gives us the equations we learn in chapter 4 come from deterministic. So in chapter 4, the equations we are going to be using to track the changes in variance, all the Arch, the GARCH models, and so on, the exponential GARCH, leverage GARCH, all that kind of GARCH that we use in chapter 4, they are deterministic. After chapter 4, we don't typically study it in this class. We study it in an advanced class. The equations we use to track the way variances change every period, okay? If it's not deterministic, if it's not Arch-GARCH models, then it will belong to the other type, stochastic. And such equations, we don't call them Arch and GARCH, we call them stochastic volatility models. So I think that's in chapter 5 or 6 of your textbook, after chapter 4. Okay? So the way variances change, if the variance of the error term in our OLS or in our how do you say, in our AR models or our ARMA models or whatever, the way the variance of the error term, if it's not constant, like we assume, there are two families of ways that the variances can change, either according to the deterministic types of equations, those are the Arch type models, that's chapter 4, or the stochastic volatility type models. That is the stochastic family of models of equations, okay? So from now on, we're going to be studying the Arch and the GARCH models. So the Arch and the GARCH models are like equation 1 that I sent you. They are deterministic, okay? They are deterministic in the sense that we don't stick in the error term, and all you have to do, give me the X. The X in the Arch and GARCH models, they are different, and that will determine exactly what type of Arch model we're using. But whatever Arch model we're using, at the end, we don't see epsilon, we don't see the error term, and therefore the variance of the error term and all that. Those belong to the stochastic volatility models. Okay, Danny, I'll stop here and take some questions before I continue.
Yeah, is there a for whatever data set we're looking at, is it possible for a data set to be at a given moment stochastic and then become deterministic, or is something just steadfast?
Okay, this is how we handle it, okay? As in the process of teaching this class, I am going to say that if you go to Yahoo, you download prices for Facebook, you convert it to return, simple return, for example, and then before you begin to run AR or MA model, whatever model you want to run, you might want to test whether the variance is homoscedastic. That is what we call the test for Arch effect, or the Arch test, ARCH. autoregressive conditional heteroscedasticity. So if we do the test for Arch effects, we're essentially testing whether the Arch model is a good model to use. If it's if we test, if we perform that test and we reject the null, where the null says the Arch is if the null says the Arch is a good model and the alternative says the Arch is not a good model, if we reject the null, then we're saying the Arch is not a good model. Okay, there could be other models. So then we go and we try to test for stochastic volatility. You understand? To see if the stochastic model is better. You understand? So the first thing in this chapter, we're going to learn how do we test for Arch effect. But your question is it possible that it will be a mixture Arch and stochastic volatility? Again, I ask you, everybody, go back to the chart, the equations I gave you in the chart, okay? If it's the first equation, the deterministic equation, you can assume that's the Arch model. But if it's not the Arch model, then if it's not the deterministic, then it is the stochastic, right? The deterministic portion is within the stochastic. Is that correct? Yes? Yeah, it is within. So if it is not, so what concerns us, it can always be stochastic. But what concerns us specifically is it deterministic? Because if the test, and some of these tests are quite strong, if the test strongly tells us, or if the test tells us that it is strongly deterministic or strongly Arch, then we don't need to waste time looking for whether it is stochastic volatility. You understand? Because if you accept that it's Arch, you fail to reject the null. That means it's stochastic volatility of some type, or it is some type of equation that is not deterministic. Okay, Danny, that's the best answer I can give you.
Wait, you said arc is deterministic or stochastic?
Arch is deterministic. It's not arc. K is arch. Chi like chia.
Yeah.
Okay, so the arch is deterministic. It's like the first equation, deterministic. Okay.
All right.
And then if it's not arch, then if it's not arch, then it can be any type of stochastic volatility. But it's like when we tested using how do you say Jacques Berra. What concerns are, is it normal? Because if it's not normal, well, it can be anything. But we test for whether it is normal. The same way we test for whether it is arch. If it is not arch, then it can be anything, any type of stochastic volatility. All right. Okay, so let's go back. It is very important to me that you follow the intuition. So Danny and Co, keep asking me the question, okay? Now, so look at this mean equation. So the mean equation can be OLS, that is, it can be Y can be sales, and X can be advertising expenditure and income of consumers and how many years of education. So it can be what you studied, like multiple linear regression in ECHO 4000, or it can be autoregressive. So in which, if it's autoregressive, then this X here and this X will be YT minus 1, YT minus 2, YT minus 3, and so on. Or if it's moving average, then the return here will be equal to it will be a linear combination of white noise errors. Or if it is ARMA, then the return at time t will be equal to a combination of autoregressive and white noise and moving average. So it doesn't matter what the mean equation is. The first assumption we make about the error term is that it is average 0 and homoscedastic. If it is not homoscedastic and it is deterministic, that is Arch type, this is the way it will change. Look at this equation 2 here. If we say the variance of the error term changes like this, it changes like the variance of the error term at any time t is equal to some constant plus constant times the squared of the error in the previous period. Look, this E is the same as this E, is the same as this E. Okay, are you looking at it? It's the same E. This E is the same as E and the same as E. So if we say the variance of E, so this variance is the variance of the error term, of this error term. If we say the variance of this error term today is equal to some constant plus some constant for today times the error term squared from yesterday or from last month or from last year, this is what we define as the ARCH1 model. So the Arch1 model says that the variance of the error term in our original mean equation, this error term in OLS, or this white noise term in autoregressive model, or this white noise term in moving average model, or the white noise term in ARMA model, it doesn't matter. The error term in our mean equation, if the variance of that error term is no longer constant, heteroscedastic, and the variance follows this equation, that if I want to determine the variance of the error term for today, I have to use this constant, add it to the error term from yesterday, take the error term from yesterday, square that error term, multiply it by this constant, add this constant, that gives me the variance today. The variance yesterday, take alpha 0, the constant, multiply it by alpha 1 times the square of the error from 2 days ago. So look, the variance of the error term today is equal to alpha 0 plus alpha 1 times the square of the previous error term. That is what we call Arch1. Look at equation 3. The variance of the error term today. Look, anytime I say variance, it is always the variance of what? Variance of this error term, this one here. If the variance of this error term is equal to alpha 0 plus alpha 1 times the square of the error term yesterday plus alpha 2 times the square of the error term 2 days ago, that is called Arch2 model. Now, if you notice, what do we notice here? I didn't put any white noise term here. I didn't add any white noise term here. I didn't add any white noise term here. So that makes this equation 2 and 3, that makes those equations what? Deterministic or stochastic? What do you think? What do you think? I didn't add any white noise here. I didn't add any white noise error term. So exactly. So that makes it deterministic, absolutely. Okay? All right.
Say that again, Professor, what you said before, Andrew.
Look, the variance of the error term here is equal to this alpha 0 plus alpha 1 times the error in the previous equation. So this error is like the X term. So this is like the Y term here. This is the dependent variable. This is a constant. You can think of the dependent variable equals the intercept plus the slope times the independent variable. But I did not add any error term here, right, Danny?
Okay. Yep, got it.
Okay. On this one, this is like the simple OLS with only one independent variable. This is like multiple linear regression, but in this case, this is our dependent variable equals A plus B1 x1 plus B2 x2. There is no error term here, okay? So these two are deterministic equations. So everything I say today is deterministic. It's not stochastic volatility. It doesn't have the error term, okay? So you can take that to the bank today and for chapter 4, Okay, so don't worry about error term, but always try to remember that. And then if the variance of the error term goes by this equation, okay, it has many. It's not only one, but it has p. Okay, thank you, William. You got it. Okay, thank you. That makes me happy that at least you guys are getting it. If you are not getting it, please speak up. Okay. If you are not asking me questions, I assume you are getting it. But Roxolana asked question, Danny asked question, Andrew, Tobias, all of you, you ask questions. I appreciate that. But some of you are quiet. That's okay. If you are quiet, my assumption is that you understand it. Okay, because I cannot read your mind. If you don't understand it, ask me a question. Okay. And in fact, if you ask me a question, I promise you, I'll buy you coffee. And if you can tolerate beer, I'll buy you beer later. Only one beer, so that I won't be accused that the professor made you drunk.
Professor,
Yes.
I have a question. So why is so I notice it's always squared. Does that mean we underestimate? That we always underestimate? Because I noticed that.
What do you mean? What is squared?
So I noticed the error term from yesterday is squared.
Yes, but
We'll always have a
hold
positive
on. But what are we estimating here? What do we want to determine? Is
The
something
variance?
squared here, right? The variance, right?
Yeah.
So to determine the variance here, we are squaring the error term. Okay. Now hold on. I will show you next Tuesday, because next Tuesday I'm going to take us back to OLS, take us back to Excel, and I'm going to run a simple OLS regression next Tuesday, and you and I will see. I'm going to collect the residual terms, okay? Because this tells me that the variance of the error term today equals a constant plus an intercept plus a slope times the error term from yesterday. But okay, let me stop here because I don't want to confuse you. After Tuesday, you will be able to see why we actually square this error term. Okay? Andrew, I ask you to please hold on till next time I do this on Excel. Okay?
That was Danny.
I'm sorry, Danny. Okay? So hold on. But okay, excellent. But for now, the Arch and the GARCH models, the right hand side is squared. But if it helps you to understand it more, you can think, because this is a squared term on the left hand side. Okay. All right. Okay. So those are excellent questions. I had all those questions the first time I studied it, but as we talk about it more, you'll come to understand it. So this last equation 4, if the variance of the error term is equal to the intercept plus, so B0 plus B1, this equation, the lag 1, the error term squared lag 1, the error term lag 2 squared, up to the error term Q, lag Q, then this will be an arch Q. Okay? An arch Q. So the Q is determined by how many lags? Guys, it is no accident that we use Q. Where have you seen Q before? When I type Arima, is Arima P, D, and what? Is Arima P, D, Q. That Q in Arima P, D, Q, what is that Q referring to? The autoregressive or the moving average? No, PDQ. Arima, ARP, MAQ.
MA.
It's MAQ.
Is MA.
Okay, it's MAQ. So the Arch model, this Arch model is really like a moving average model. Remember, when I showed you moving average last week, I said the moving average is XT equal to, a constant and is it theta or phi? Theta times the error term. Remember? White noise term. If you don't remember, just hold on. I'm going to show you right now. Okay. So everybody hang in there. Don't get confused on me. But I want to show you that the Arch model is really a moving average type model. That's why it is no accident. That's why we always say arch Q. Okay, now, so hang in there with me, everybody. Okay, please hang in. Let me go back to what we have done before.
Professor, you said it's no accident. What?
It is not an accident. It is not random that we are using Q. We say arch Q instead of arch P. If we had used arch P, then we're saying the arch is like a autoregressive model. No, the arch is like a moving average model. Okay, it's just the difference is we square the error term. Just hold on. Okay. All right. Look at this handout. All of you, you have this already. I used this to when we were studying the autoregressive model. Look, an AR1 process is xt equal to some intercept, some constant plus slope times xt minus 1. So there's x on the left-hand side and there's x on the right-hand side, and there's this error term, yeah, right? So this is an AR1 model, right? Everybody agree, correct? Somebody talk to me. This is an AR1 model, right? There's x, there's x
Yes.
here, there's x here, and there's x here. And if it's an AR2 model, we'll add on another, phi 2 times xt minus 2. That would be AR2 model. If it's an ARP model, then we shall keep adding lagged x until we get to p lags. So for AR, we say ARP. Okay, good. So let me show you now an MA model. We studied this last week, okay? An MA model. Okay, this is an MA model. We studied this last week, so. So what is an MA model? XT. Anybody tell me, do you see XT lagged on the right-hand side? Anybody tell me, yes or no?
No.
No, absolutely not. What do we see on the right-hand side? We see XT
Error
here
terms.
is error terms. We see intercept here plus error term in this term, white noise error term today plus slope times white noise error term from yesterday plus slope times white noise error term from 2 days ago up to Q lags. So this is like the Arch model. So the Arch model says something variance here equal to intercept plus some lag term of the error term. So on the right-hand side for the Arch, there we have only error terms. Okay, good. So the Arch model, you can think of it as a kind of moving average, but of course we're squaring the error terms because the variance term is squared on the left-hand side. Okay, good. Okay, so let me show you one more thing, okay? And then I didn't show you this last week because we ran out of time, but I had suggested you guys go read it because there's really not much to it. I'm not going to I'm not going to belabor it too much in this class because we don't have time. Now, this is, you guys, you have this from last week. This is an Arma model, A-R-M-A. Arma means there has to be an autoregressive portion and there has to be a moving average portion. The autoregressive portion we represent by P. How many lagged autoregressive terms are there? How many moving average terms are there is Q. So the ARMA model is xt equal to intercept plus the autoregressive component. You see that, right? Everybody see that? There are P lagged X terms. So this is X. Today is determined by xt minus 1 lagged 1 period, lagged 2 periods, plus lagged P periods. So if this P is 4, then this would be Arma 4, comma. Okay, so we have P terms of the X term here. That makes it autoregressive to P order. and then plus moving average. So this is the moving average portion. Okay, so this portion contains only lagged error terms, white noise terms. How many of them? Not one, not two, but maybe four, in which case Q is 4. So Arma 4, let's say Arma 4, 5, meaning we have 4 lagged X terms plus 5 lagged white noise error terms. So Arma 4, 5, meaning the autoregressive portion is 4. There are 4 of them, and the white noise error terms Q, there are 5 of them. So that's an Arma model. Okay, everyone. I had asked you to read this. This is from last week.
Professor, I have a question. So
Yes.
there's a model that's ARIMA, right?
Yes, there's a model that's ARIMA. The I.
What is the I? Yeah.
That I is the order of integration. So if it's ARIMA and the I is 1, it means that the return, the price, the return equation is not stationary, but the way to make it stationary is you difference those return one time only. So that I is represented, that I represents how many times do you difference. What do I mean by difference? You remember last week I showed you that thing called diff, D-I-F-F. Remember that? For your homework 3.
For GDP, right?
Yeah, for the GDP equation, I use the DIFF. Differencing meaning, you see how you calculate simple return. Return today minus return yesterday divided by return yesterday. That is a simple return over one day. Is that correct?
Yes.
Okay, but what is diff, D-I-F-F? Difference, meaning return today minus return yesterday. You don't divide, you don't convert it to percentage. That's difference. You understand?
Yeah.
If let's say you and I, we go to Yahoo, we download IBM prices day by day for 10 years. And we calculate the daily simple returns. And the daily simple return, we apply the unit root test, ADF, augmented Dickey-Fuller test. If we apply the ADF test and it tells us that it is unit root, that is, it is not stationary, it's unit root. But it turns out that if we difference those returns, if we take return in time 2 minus return in time 1, return in day 3 minus return in day 2, return in day 4 minus return in day 3, return in day 5 minus return in day 4, and we do that all through the 10 years of daily data. And then we take the new column called difference that we obtain, and we apply the stationarity test, and we see that the difference column is stationary. That means the return was not stationary, but when we did diff, when we difference the return, the new column we get is stationary. That means all we needed to do is difference the non-stationary data. We difference it one time to make it stationary. Then, Andrew, the I in ARIMA will be equal to 1.
Makes sense.
Sometimes for some type of nasty data, for some nasty variables, if you convert the return, if you calculate the simple return and you test for stationarity, the simple return is not stationary, and you difference it one time, Andrew, and the difference, the one-time difference column, you test for stationarity, it is not stationary. And then you difference that difference. So you are differencing the original return, you are differencing it 2 times. The second time you get the column and you test for stationarity and it is stationary. That means our I is 2.
Professor, does it always converge to stationary?
Yeah, well, you can difference it many, many times and it may not be stationary. But generally for financial time series, are you with me? For financial time series, that's why we have a course on financial econometrics because the stylized facts for financial time series, one of the stylized facts, generally when you difference one time, you get it to be stationary for financial time series. It is one of the stylized facts, okay? All right. Sometimes there are some data that you difference 2 times, is still not stationary. You difference it many times, it is not stationary. But for financial time series, in most cases, when you difference 1 time, it is stationary. Okay, somebody is asking me a question on chat. Who's that? Okay, okay. All right, so listen. So this is an ARMA model, folks, okay? ARMA combines the lagged, look, this is X on the left-hand side, and on the right-hand side, we see the lagged X. Plus, it also has the lagged error term. All right. Okay, okay. Now let me just show you. I'm running a little bit out of time, so let me go back and show you. So everybody knows that I have shown you now that, look, on this, this is the Arch models, right? This is the Arch model. So if, look at the equation 2, look at equation 3, look at equation 4. Do you see this variance term? Do you see this variance term on the right-hand side? Anybody tell me yes or no?
Yes.
No?
Oh,
This variance term, you don't see it on the right-hand side.
no.
What do
Oh,
you
no,
see?
no, 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 it's not.
What do you see on the right-hand side? It's only error terms, right?
Yeah,
So
Okay.
is it like autoregressive or like moving average?
autoregressive,
No? If it's autoregressive, then I will see this
same,
Moving
right?
average.
then I'll see this
Model.
sigma
Right.
on the right-hand side. It's moving
Got it.
average type, okay?
Right.
I'm just trying to help you remember, okay? It is like moving average. That's why we use the Q instead of the P. Now, bear with me now.
Wait,
Let
Professor,
us,
I have a question. What does the AR stand for in Arch? Autoregressive, right?
autoregressive conditional heteroscedasticity. It is because we are regressing something, okay? Okay, it's autoregressive because you see, this is the variance of the error term. We are regressing the error term. So again, just can you hold on to that question? Because I don't want to confuse you for now. But that's a great question. Thank you. Okay, that's an X. So, but before I run out of time, I want to show you another model. Everybody, you have this already. It is page 4 of it is the 4th page. So let me look for it. Hey, Ian, my buddy, I just noticed you. How are you doing? Okay. So let us look at this equation, everybody. Look at this equation. This is page 4. You guys crack me up. This is page 4 of the handout. So on the Arch equation, on the Arch, if you go to the course document, I gave you 4 pages. The 4th page, look at. Okay, so for this thing I call GARCH. Look at the GARCH equation. So who was asking me what is the AR portion? Look, on this equation 2 here, what do you see in equation 2? The variance. Look at the sigma squared. Do you see sigma squared on the right-hand side here?
No,
Yes.
Yeah, this is sigma squared, but lag.
that's not the same lag though.
No, it's not the same lag. But for AR models, when you see the XT on the right-hand side, is it the same lag? No.
No.
No, it's not the same lag. But what bottom line here is this: I see sigma squared here on the left-hand side. Yes, it is sigma squared today, T, but I also see sigma squared lagged on the right-hand side. Are you with me?
Yep.
And then we combine it with the error term on the right-hand side, lagged. That's GARCH 1. So GARCH, so that we put G here. Whenever you see G, it means GARCH, generalized autoregressive conditional heteroscedasticity. That's what it means. And whenever you see G here, it means we have not only the error term from previous, we also have the sigma squared, the variance of the error term from previous. Here we have the error term lagged one time. We have the variance term lagged one time. So that's why you can never see GARCH 1 or GARCH 2. No, it is GARCH 1, 1, GARCH 2, 2, GARCH 3, 3, and so on. Because for GARCH, we have a combination of the error term on the right-hand side lagged and the variance of the error term on the right-hand side. So from what you have learned now, is this GARCH, and by the way, equation 3 here is GARCH what? 2, 2, because we have the error term lagged twice, and we have the variance term lagged twice. So this is GARCH 2, 2. This is GARCH 1, 2. We have the error term lagged only one time, and we have, I'm sorry, we have, I made a mistake here. This should be GARCH, yes, this exactly, okay.
Should be 2, 1.
No. This is GARCH 1, 2, because the P, that's why I put it here, I'm sorry. Because the P term always comes first. So it's GARCH, it's usually GARCH PQ. Okay, that's why I put this here.
It's a bit confusing, Professor.
It is confusing, but you have to get used to it. That's what we do in this that's what we do in the profession. So
But it's cumulative, so you can put it any way because it's addition.
Yeah, you can do it GARCH QP, but we don't write it like that. Okay, we always put the autoregressive term first, the P first, and then the Q. But the Q term refers to the error term. So here I have two error terms. Remember, we use Q to represent the error terms. That's why we put it Q here too. And then the variance term, the variance of the error term, there's only one of it. That's why I put it here. It is confusing. That's why I'm kind of alerting you. So you will see GARCH PQ. The P represents how many terms of the variance equation, how many terms of the variance of the error term is lagged. And then the Q represents how many terms of the error itself is lagged. It is confusing, but that is the convention in the profession, okay? So look here, equation 5 is GARCH PQ, because in this equation 5, we have P. You see this variance of error term, sigma squared, we have P sigma squared here, lagged. Sigma squared, sigma squared, sigma squared, T minus P. So that P comes first, okay? And then the error term, this error term squared, there are Q of them, and that comes second, okay? So GARCH PQ meaning, so GARCH 3, 4 means there are 3 lagged variance terms, and then there are 4 lagged error squared terms. Okay, guys? All right. So just give me one more minute, everybody, and let me say the last thing. And then, by the way, everybody in this class that sent me your homework 3 directly to my email, or you did not submit homework 3, please wait after class. After this class, I need to talk to you for only 5 minutes, I promise, okay? So all of you, whether I asked you to or I did not ask you to, all of you that submitted your homework 3 either late or you sent it directly to me for whatever reason, whether I allowed you to or I did not allow you to, wait in this class for 5 minutes. I need to talk to you, okay? Yes, Danny, blame Professor Boleslav. Okay, actually, we have invited him to my department more than one time to give us a lecture during the week. So next time I'll let you guys know. Now, and everybody, please tell me the GARCH model. What do you think? Is it like an AR model, or is it like an MA model, or is it like an ARMA model? What do you think?
Arma.
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 Exactly.
Arma.
You guys are fantastic. I'm going to have one glass of champagne after this class, okay? Because you just made my day. So anytime I say Arch model, ARCH, what type of model is it? Is it AR model or MA model type? Arch is an MA type model, is that right? And anytime I say GARCH, GARCH is like an ARMA model. Excellent. I clap for everybody. Okay, so I am going to stop recording. Oh my God, I shouldn't be clapping when I'm recording. I should be, serious. I'm going to stop recording now.
The recording has stopped.
Okay, so guys, thank you for your attention. I'm sorry I had to speak very fast, but this is everything there is in chapter 4. Next Tuesday, I will show you how we test for whether there's there's arch effect, how we test for whether the error term in the mean equation is homoscedastic or heteroscedastic. I will show you, and maybe actually this weekend I will post an arch commands, some few commands that I will run on Tuesday. If you have time, run it yourself. If you run into problems, it's okay. You can email me, or don't bother. On Tuesday, I'll run it and then we'll figure it out. Okay, everybody? Okay. Thank you. I'll see you next.
Professor, I have a question
Yes.
about the project.
Oh, hold on. All of you, if you don't have a group yet, individually, if you don't have a group yet, please tell me, send an email to Chan, our TA, and copy me. Because so far, we have all those people who have formed teams of 2. Some of you said, Professor, help me, put me in a team. That's okay. But if you don't have a team yet, whether you have sent me an email or not, send an email to Chan, the TA, and then CC me. Because now Chan and I, we are going to put you in teams at random, okay? Okay, so please do that. And then I will post the project sometime tomorrow, okay? I just need to look at it and then look at the data, make sure it's clean for everybody, and then I'll post the project tomorrow. Okay, everybody? But for tonight, I want to see only those of you who either sent me your homework 3 directly to my email, whether I gave you permission or not. It's okay.